All right, picking up where we left off, so we're going to finish 1.2. So in this section, we're talking about the graphs of functions. And so we were finding the domain and range. So remember, the domain is the spread left and right along the x-axis, the x values, range are the y values. So the lowest value and the highest value when we're talking about a graph. So where we left off yesterday would be here looking at this graph. So we have a parabola that's facing downward. We can see that it continues down into the left forever and it continues down into the right forever. Both of those things are going to be important as far as affecting what our domain and range are. So generally when we're finding domain and we're looking at a graph, we want to see if there's kind of an endpoint to our graph, if it kind of approaches an asymptote or something else. In this case, I'm not seeing anything that would indicate the graph ending, right? It looks like it's going down and to the left, so it's going to keep going this way to negative infinity. And the same way on this side, it's going down and to the right, so it's going to keep going to this side to positive infinity. So using interval notation, we would write our domain to say it's from negative infinity all the way to positive infinity. And we always use parentheses with that because infinity isn't really a number that our graph can reach, so it approaches that value. Another way that we might see this written is simply all real numbers. That's another way we could express this. All the real numbers are valid inputs, are valid x values for this function. Now, the range, looking at that, we do appear to have a highest point. Our graph appears to not pass above this right here. This would be our maximum up at 4. However, since the graph is going down forever, the lowest value is going to be that it approaches negative infinity. So when we go to write our range, we're going from negative infinity up to 4. We want to make sure we're including 4 because our graph does actually have a point up here. So the bracket for 4, but not for that. Another way we might write this using inequality symbols is we might say that the range is y is less than or equal to 4. The y values are less than or equal to 4. We can use that way to also express our range. So I'm going to clear this. Check to see what I had as my answers. And yeah, same idea. All right, the next important concept that we had were the idea of increasing, decreasing, or constant. So a graph is increasing as we move from left to right if it's simply going up. That's increasing. It's constant if it's perfectly horizontal, and if it's going down, that means it's decreasing. That's kind of the simple way to think about it. There is a more complicated formal definition for that that would say something like a graph is increasing if and only if for every two x values, if one x value is greater than the other, then the output for that x value is also greater than the other output. So like if we look here, for x is equal to -5 and x is equal to 4. So the output for -4 is greater than the output for -5. And that would have to be true for every pair along this interval for it to be considered increasing. That's a pretty formal definition, and we're really mostly going to be just looking about whether it's going up or going down or constant. All right. So moving on to our next slide, we can actually look at an example. So just kind of really quickly, what we can do with this is just, write some letters here to say whether it's increasing, whether it's constant, or whether it's decreasing. So for this first one, we've got an increasing section here. We're starting down here and we're increasing. Right here, we're constant, with two perfectly horizontal, and then we're decreasing. Now, when we go to write these intervals, we're talking about the intervals along the x-axis, the intervals along the x-axis with which it's increasing or constant or decreasing. So this interval would be from -3 to +1. That's where it stops. Now we don't include the endpoints, even though there are closed dots there, because at the ends, the graph is neither increasing or decreasing, right? Because once we reach 1, it's kind of stopped. Now it's kind of changing over. It's no longer increasing at this point. It's stopped increasing. It's reached its sort of peak, and now it's entering a new phase. And then here we are constant from 1, right? 1 to 3. 1 to 3. And then we start decreasing. So at 3, we're decreasing until 5. 5 is when it stops again. So those should be our intervals for that one. Now this was a piecewise function. This one is a more standard smooth curve graph. You'll notice on these types of graphs, we don't really have constant intervals. Another thing with them is these arrows can kind of confuse people. They say, oh, it's pointing up. That means that it's increasing on these ends. But remember, we actually have to read the graph from left to right. So here, we're actually decreasing, despite that interval pointing up. We're decreasing until right here, where we switch over from decreasing to increasing. So this interval is increasing until about here, where it stops, and then it becomes decreasing again until here, right? It's decreasing, and then it starts increasing again over its final interval. So there's 4 different alternating intervals. It's decreasing and increasing and decreasing and increasing. And we just want to express those. For this first one, the left side is negative infinity, right? It's going up and to the left, it's negative infinity. We just have to assume it keeps going that way forever until 1. 1 is where it stops decreasing and it starts increasing. So from 1 to 3 is where it stops increasing again. And then from 3 to 4, it's decreasing. Right? From 3 to 4. And then from 4 on to positive infinity. Again, we have to assume that it keeps kind of following this direction up and to the right forever. So to the right forever would lead us to infinity. All right. So those should be our answers. We can go ahead and check that real quick. Here's our intervals. And then on the next one, again, here is our intervals. And yeah, it looks great. So I'll clear those and move on. All right, so the next thing we have are relative minimums and relative maximums. So the point at which a function changes from increasing to decreasing is going to leave us with a relative maximum, at least the highest point in the area. Now, we use the word relative to mean that it might not be the highest, the absolutely highest point on the graph. And in this case, it's not, right? This is a relative maximum. There are many points, actually an infinite number of points that go higher than that. But if we just look at the neighborhood around it here, it's the highest one. It's relative to its neighbors. It's the highest point. Same down here, we have a relative minimum. This is the lowest point around it. If we just look at its immediate neighbors, it's the lowest point around it. It's not the lowest point on the graph because this graph goes down forever. So these are what we call relative minimums or relative maximums, or generically relative extrema. Minimums and maximums are extrema, extreme points. Well, another way that we can think about these is for maximums, I like to think of them as the top of a hill. Here's a little hill and the maximum is the top, or the bottom of a valley. Here's a little valley and this is the bottom of the valley. So here's a nice graph for us to look at and identify some relative minimums and maximums. And well, it's easy enough to look at it. We can see that we have a valley down here. So if we look in this area, this would be our relative minimum. And then here we have a top of a hill right here. And then up in this neighborhood, this is our highest point. That's going to be our relative maximum. When we talk about the values of those, we're looking at the y values. So this one would be at 4. And this one down here looks to be at -8. So let's go ahead and check that. Yeah, so we have a relative maximum at 4 and a relative minimum at -8. All right, the other way we can do this is we can use a graphing program like Desmos to help us figure out relative extrema as well. So I'm gonna go ahead and type this function into Desmos. So I'll have to minimize my presentation. And Desmos is gonna identify these extrema for us automatically. That's a +x. Okay, So you'll notice it puts points for us at points of interest. So at any place that it crosses the x-axis, and also at these relative minimums and maximums. So here we can see, just by clicking on those, we can see the relative maximum. This is a rounded value. This decimal would actually probably be going on forever, but 0.385, and then at negative 0.385. So these are our two relative extrema for this problem. And it's easy enough, finds it pretty much automatically. Other handheld graphing calculators, you'll have to kind of tell the calculator to compute it for you, but Desmos does it pretty quickly. All right, so go ahead and move on from here to our last concept of even and odd functions. So even functions are symmetrical about the y-axis. For every x value, f of x is going to be the same thing as f of negative x. So which that sort of means that if you put in f of 2 into a function, that's going to give you the same output as if you put in f of negative 2. 2 and negative 2 are just an example. It could be any positive and negative number that are the same digit. So f of 5 and f of negative 5, f of 10 and f of negative 10. If that's true for all values of x, then we call it an even function. For an odd function, it's a little bit different. It's symmetrical about the origin. It has sort of a rotational symmetry, or if you draw the 2 points that are symmetrical to each other would be, if you draw a line from that point through the origin, you'll hit the other point, and that's true for all of them. It's a little trickier to see that, but I'll show it here in a minute. Mathematically or algebraically, what it's going to look like is f of negative x is equal to the opposite of f of x. We'll look and see what that actually looks like, but for instance, if you put in f of negative 5, that will give you the same output as if you put in f of 5, but take the opposite of your answer. Weirder, but also we'll see what it looks like. All right, so here's an example of two graphs. The one on the left here is an even function. So you can see these 2 points are symmetrical across the the y-axis here, and all points are going to have a symmetrical partner across the y-axis. But in particular, this one is at -1 and this one's at +1, but they have the same output of 4. That's what we're talking about. For every input, the opposite input is going to give you the same output. Kind of a weird relationship, but pretty useful. It's actually useful to know whether a function is even or not, because that lets you know a lot about the inputs and outputs of it. Odd is a little bit stranger. You can notice these 2 points, if I can connect them, and they pass right through the origin. These two are symmetrical for each other. And then these 2 points here also are symmetrical. There's a line that would connect them that is directly through the origin. And you could actually pick that out, that any of the points are going to have that property. So if I pick a point on here like right here, and I draw a line through the origin to the other place right here, notice that those 2 points, this one right up here, this one here, and this one here, are symmetrical through that origin. If you just reflect directly across the origin, there they are. These points, they reflect directly across the origin. Even C and D reflect directly across the origin. The other way you can sort of visualize it, if you take half of your graph here and you rotate it 180 degrees, it would end up lining up exactly on top of the other half. Has that sort of rotational symmetry or symmetry through the origin. A little bit harder to see though. It's not quite as easy to see that's what's going on as the direct symmetrical across a line. All right. So again, notice how this graph's symmetrical across the y-axis. This one has that 180-degree rotational symmetry. All right, so let's go ahead and look what happens when we talk about it in terms of an equation. If we have the equation, how do we decide? So for an even function, f of x is going to equal f of negative x. And for an odd function, f of negative x is going to equal the opposite of f of x. So algebraically, we can quickly show that. So looking at this one, is this function even, odd, or neither? With polynomials, what you can do is actually look at the exponents to give you a bit of a hint. If the exponents are even, then I should test to see if it's an even function. 3 is not even, so I'm not going to even test an even function. If the exponents are odd, I'm going to test to see if it's an odd exponent, or if it's an odd function. If I have a mixture, I actually am pretty sure it's going to be neither, but I'll go ahead and show either way. So let's look at this one. I'm going to be testing to see if it's an odd function. So again, I want to show that the f of negative x is the same thing as the opposite of x. It says f of x and our function's called g of x. That's just a name like f or g. That doesn't really affect anything. So I'm going to figure out what g of negative x is equal to. Well, that just means I plug in a negative x into all these places. And so everywhere there's an x, I put a negative x. Well, this is really negative x times negative x times negative x. A negative times a negative times a negative is a negative. So this becomes negative x to the third. And then here, minus negative x, that just becomes plus x. So with a little simplifying, this is what we end up with, that g of negative x equals this. Well, now let's figure out what the opposite of g of x would be. Well, really, that just means I'm going to distribute a negative to the whole function, the whole original function. So I'll take that negative sign and distribute it. So that becomes negative x to the third plus x. And so you can see now that these two things, g of negative x is the same thing as negative g of x. So that satisfies the algebraic definition of what an odd function is. So we'd say that this function is odd. Now, we can quickly just show, examine what we've already done to show that it's not even, right? G of negative x is this thing right here. And it's not the same thing as the original function. It's a little different. It's not, doesn't have a negative here, right? It's not the same as the original function. So we definitely know that it wasn't even. And so it's an odd function. Okay, I'm going to go ahead and move forward and do another example of this. All right, two more examples of even and odd. So again, these are both polynomial functions, so I can quickly just decide what to test or not. So if the exponents are even, then I'm going to see if this one's an even function. And if the exponent is odd, I'm going to see if it's an odd function. And again, really just the highest exponent is the only one I'm really talking about. So again, for an even function, I'm looking to see, since this is h of x, I want to show that h of x is the same thing as h of negative x. That's how I'm testing an even. For an odd, since this is odd, I'm going to be testing to see that f of negative x is the same thing as the opposite of f of x. So I'll go through these two things. So now we already know h of x. We already have h of x, so we just need to figure out h of negative x. Negative x squared minus 1. So negative x squared means negative x times negative x. A negative times a negative is positive, so h of negative x is really just x squared minus 1. But now we can see that these two things are the same, that h of x is the same thing as h of negative x. So this function is even. Pretty simple. Next one, again, because we have an odd power here, I'm going to test to see if it's odd. So f of negative x is negative x to the third minus 2 times negative x plus 7. A little simplifying here. This is negative times negative times negative. So we're going to put a negative x to the third. Negative 2 times negative x is plus 2x plus 7. All right, and so that is f of negative x. All right, so I've got that part. I know f of negative x. Now I just need to know the opposite of f of x. So I'm just going to kind of quickly do that. A negative means that I just need to apply a negative to everything here. So that makes this negative, positive, and negative. Right? That's how that's changing. It's just changing the sign of each one. It's essentially distributing a negative to the whole function. Now we want to check, are these two things the same? And they're very close, very, very close, in fact. The first term's the same, the second term's the same, but this one, it's not the same. It's plus 7 here, but it's minus 7. It's very close. It is not an odd function. So in this case, we know that it is neither. It is neither even or odd. And a lot of functions are going to be neither. Okay. The drawings. And the homework. So make sure you do these homework problems and then come to any of the open office hours Wednesday and Friday at 1:30 if you have questions and need help.